Hello, my name is Jolene Rhodes, and today in this lesson we're going to talk about volumes of solids of revolution using cylindrical shells. Now, a cylindrical shell simply looks like a can without the top and without the bottom. And in order to talk about finding a volume of solid of revolution, what we first have to talk about is what's the volume of one of these cylindrical shells. To me, the easiest way to envision the volume of a cylindrical shell is to actually envision cutting open this can and laying it flat. If you did that, what you would have is you're going to have a rectangular solid that is simply going to have a length, height, and some thickness here. So what we're going to have when we cut this open and lay it flat is we'll have a region that looks like this. Now, if we envision this, the length of my rectangular solid is the same as the distance around this cylinder. Now, the distance around the cylinder, that's a circle. Distance around a circle is the circumference, and the circumference of a circle is 2 pi times the radius. So we've got some radius in here, and what we have then, the length of this rectangular solid is 2 pi r. Each of these has a height, so let's label that height. And we also have some little thickness to both of these. So we've got this little thickness on this one, we've got this little thickness here. And thickness that we've used in any of similar integrals in like Riemann sums or volumes using disks and washers, we've designated this thickness as either the change in x or the change in y. So either delta x or delta y, depending on the orientation of the shells that we are constructing in our problem. Now, if we look at this, then the volume of a rectangular solid is its length times its width times its height. So in this case, it's the circumference times its height and times its thickness. And if we look at the picture above, the circumference is 2 pi r, the height we've designated as h, and our thickness is either dx or dy, depending. Now, what we want to do to actually find the volume of our solid of revolution is we're going to add all of these up. So what we're going to end up with for our final volume of our solid is the formula we need is going to be the integral from some a to b of 2 pi r h, and then either times dx or dy, again, depending on the orientation of the problem. So what we're going to do now is look at some examples so that we can figure out how to find actually the r and the h, and when we use integrals in terms of x's and in terms of y's. So let's look at a few examples. So as our first example, let's use the region that's bounded by y equal to the square root of x, y equal to 0, and x equal to 4. And what we want to do is revolve this about the y-axis. So we're going to take the region that we see here, and what we're going to do is revolve this around the axis, which means that the first thing I want to do is, of course, spin that around the y-axis, and so what I get is a matching region on the other side. Again, three-dimensional object, so let's see if we can't make this look a little bit three-dimensional. So we're going to get this little three-dimensional object in here. It's got flat sides, it got curved in the center, and what we're going to do is find the volume of this. Now, we are going to, with shells, remember we're going to look at stacking cans inside one another. So what happens when we look at a picture like this one and we look at a region like this one, what we actually do is we're actually going to slice this in the x direction. Now this is opposite disks and washers. So if you've already learned about disks and washers, you would have sliced this in the y direction because we're spinning around the y-axis. The idea of cylindrical shells is the region actually gets sliced in the opposite manner than disks and washers do. So if the integral does not turn out well in the one variable when you're trying to use disks and washers, switch to the other variable and switch to using shells, or vice versa. Sometimes one method works a lot better than the other, And sometimes we can't do the integral at all one way or the other, and sometimes you could actually find this both ways. But you should get exactly the same answer. It's the same volume. So we are going to slice this as I've drawn a sample slice. And what we're going to do is envision spinning that around this axis. Now, if we envision spinning that around the axis, what we're going to get is the matching slice on the opposite side, and we'll get this can-shaped region. Again, here we go. Little can-shaped region that's in here. And what we're going to do is we'll have a bunch of those. So I'll have that one, and I could have another one right here, a little taller one. And again, its other side would be here. So we'll get this region that's here. And you're going to get these little stackable, they're kind of like stackable cans. So one goes inside the other, goes inside the other. And we envision looking at those. Now what I want to do is look at a sample can. This one maybe right here in the middle. And let's see if we can identify the pieces that we need. We need to talk about its circumference, we need to talk about its height, and we do know the thickness, but we can talk about that too. So now what I want to do is, in finding the volume of this solid, what we're going to do is we need to, now again, what I said, look at the way these cans are stacked. They're stacked one inside the other in the x direction. So our integral in this case is going to be in terms of x's. Our limits of integration, again, then are in terms of x's. Well, where's the first can? Well, the first can is right in here at 0, and our last one, the outer edge of this solid of revolution, is out here at 4. So our integral is going to go from 0 to 4. 2 pi is a constant. You can either put it in your integral or in front of your integral. It is a constant. Now, the radius of each of these cans, here's the radius of this can. Here is the radius of that can. Here is the radius of the outermost can. And what you need to realize is what? We're going to have a can of every radius from x equal to 0 to x equal to 4. So the radius of the can is simply the x value of where you're located. So what we're going to do then, the radius is just x. The height of each of these cans, remember height is here, so the height of each of these cans varies, but what does it vary with? Well, it varies with wherever our function is. How high is our function? And in this case, our function is given by the square root of x. So the height of each of these cans is the square root of x, and our thickness is our dx that we need in order to do this integration problem. So the volume of this solid then is 2 pi, our radius, which is x, times our height, which is the square root of x, times our thickness, which is our dx. Now we can go ahead and do this integral. This is going to be 2 pi. This is the integral from 0 to 4 of x to the 3/2 power, if we combine our x's together. And if we integrate x to the 3/2 power, we're going to get 2 pi. Integral of x to the 3/2 is 2/5 x to the 5/2. Evaluated from 0 to 4. And if I simplify that, if we plug in 4, we're going to get 2 pi times 2/5 times 4 to the 5/2 power. And then minus, we plug in 0 to that, we are going to get 0. So our final answer here then is, which is 128/5 pi. Okay, and that's our volume of that particular solid. Now let's look at the same picture, same original region, but let's instead spin it about the x-axis. Okay, so we're going to look at y equal to the square root of x, y equal to 0, which is the x-axis, x equal to 4, and we're going to rotate this about the x-axis. So our picture looks like this one. Now again, what I want to do is draw in a sample cylindrical shell. We are going to, when we look at shells, remember, we're going to actually stack them the opposite you would have stacked discs and washers, or we're actually going to stack them opposite of the axis that we're going to rotate around, because the shell itself rotates around the same axis. So when we cut our object, we're going to cut our object in the same direction that we've drawn so that we can take this piece and we can rotate it around the axis the same as the entire region was rotated, so that we end up with these shells that stack one inside another. Now here's a sample shell for this particular region, and again, picture a whole bunch. There's several that are smaller, and there's several that are taller and smaller, so I could put another one. I could slice this here, and we could put another little cylindrical shell in here. So we've got a couple of them. They're just going to stack one inside the other. Now again, in order to be able to find the volume, what we're going to have is we're going to have the circumference, which is 2 pi. We're going to need a radius, a height, and a thickness. And first let's look, and our integral, because we are rotating about the x-axis, our integral is going to be in terms of y, or if you look at your cans, notice my cans are stacking up here in that y direction. So I'm actually slicing in terms of y's. Now my y values then, the very innermost can would be at 0. The outermost can is going to be at this height right here. Well, if we look, we had x equal to 4, and we have the function y equal to the square root of x. So when x is 4, y is 2. So our cylindrical shells are going to go from 0 to 2. Now, again, what we're looking at then is the radius of each of these. And if I look at the first one I drew, the radius of this is measured from the x-axis up to our can. If we look at each of these radii, the very first can has just a radius of 0. After that, we're going to have radii of every single value up until we get to 2. So the radius of each of these individual shells is just whatever the y value is at that point. Now the height of each of these shells, let's look at the height of this particular shell right here. So let's look at the height of this shell right here. Now the height of that shell right there goes from here to there, and we want the height. So height, if you look at measuring things on any kind of coordinate system, if we want to find the height of that, we actually need to find the difference between the two distances away from the y-axis. This height here, the furthest we're away from our axis, is 4. So our height in this case starts, if we look, all we want to know is how long is this. So it's basically 4, which would take us this whole distance all the way back to the axis, and then we want to subtract off this little distance right here, but that little distance is our function value. So my height is 4 minus whatever my function value is there. Now keep in mind our integral is in terms of y's. So as we had y equal to the square root of x, x is going to be equal to y squared. So our height then is the distance 4, so from the outermost point all the way back to the axis, minus this little piece right here, and that will give us the difference between the two. And that gives us our integral set up for this particular volume using shells. And then we can, in order to integrate it, we are going to distribute that y through. So we'll be integrating actually 4y minus y cubed with respect to y. And then we can integrate each piece. So we're going to get 2 pi integral of 4y is actually 2y squared, minus the integral of y cubed is 1/4 y to the 4th power. We're going to evaluate this from 0 to 2 by plugging in our 2 and then plugging in our 0, and we'll get a final answer of, which gives us an answer of 8 pi. Okay, now let's look at some more examples. Okay, let's look at the graph y equal to x to the 4th. Looks roughly like this. Y equal to 0, which is the x-axis. X equal to 2, which is a vertical line out here at 2. What we want to do is rotate this region about the y-axis. So we're going to rotate this way about the y-axis. We'll get another region that's over here. And we want to then draw in a sample shell. I want to draw in a sample shell, so let me put one right in here. There's one. matching side over here. Okay, so here's our sample shell. And again, so we want to set up our integral for our volume as we are rotating about the y-axis. And again, you can see that my shell is oriented vertically like the axis. And if we look, here's the outermost shell out here. If we look at those shells, what we can see is our shells are stacking actually along that y-axis, which means they're stacking in the x direction. So again, we're going to spin around the y-axis. Our integral is going to be in terms of x. And we're going to have 2 pi. We need the radius. Again, the radius of each of these shells is just whatever the x value is, as x varies between 0 and 2. So the innermost radius is 0, outermost radius is 2, and in between it's whatever the x value is that is associated with that particular shell. So our radius is x. We need to then look at the height. Here's our different heights. And the height of this particular graph is just given by our function, whatever our function value is. And our function value in this case is whatever x to the 4th is. So we're going to have our radius, which is x, our height, which is x to the 4th, and our thickness, which is our dx. And now we have the formula filled in. We have 2 pi r h times the thickness. And so what we're really just doing here is integrating. We've got 2 pi times the integral from 0 to 2 of x to the 5th dx, or 1/3 x to the 6th, evaluated from 0 to 2. Oh, don't lose the pi. So actually I have 1/3 pi x to the 6th, evaluated from 0 to 2. If we plug in 2, we get 2 to the 6th power, which is 64. So we're going to have 64/3 pi as our volume of this particular solid or revolution. Now what I'd like to do is take that same problem again, except what I want to do is spin that region about the x-axis instead. So same problem, but about the x-axis. And let's look at what that would look like. So let's take our region that we had, which was y equal to x to the 4th, y equal to 0, and x equal to 2. So we have this picture. We're going to spin this about the x-axis, which means we're going to get a region that looks like this one. Okay, which is kind of funnel shaped, I guess. And what I want to do then, again, sample shell. As we're spinning it about the x-axis, remember our shells also want to rotate around the x-axis, so we're going to slice this in the y direction. Okay, so here's our sample shell. I would always draw a picture on these. I think you need the visual. And so let's find the volume of that. Now volume is going to be 2 pi. We are rotating about the x-axis, which means if you picture my shell, it's they're going to be stacked. If I stack a few of these, they would be stacked in the y direction. So I've got in all my shells, they're stacking in the y direction. So our integral is going to be with respect to y. We've got 2 pi. The y values are going from where to where? Well, my y values are going from 0 up to this point right here. Well, this is where x was equal to 2. My function is x to the 4th, so my y value up there is going to be 2 to the 4th, or 16. So I'm going to go from 0 to 16. The radius of each of these shells is, again, just the y value. We're going to have y values that range from 0, radii that range from 0 all the way out to 16. That's our biggest radius of the shell. That's going to be all the way out here at the end. And then the heights of these shells. So again, let's look at the height of these shells. The height of these shells are, again, what we want is this little region right here. Now if I picture that, what I want to do, if I look at 2 gets me all the way from the y-axis out to the outer edge. But then what I want to do is subtract off that piece that's inside there that it doesn't count, because remember my shell is right here, just this little piece right here. So the height of that then is 2 minus this little piece right here, but this little piece changes depending on where we are. That little piece is whatever our function value was, and our function value, again, remember our integral is in terms of y, so if we had y equal to x to the 4th, what we need to do is solve x for y, solve for x in terms of y. So if y is equal to x to the 4th, x is going to be equal to the 4th root of y, or y to the 1/4 power. So what I'm going to have is 2, the distance 2, minus the function value, which is y to the 1/4 power, and we will then end up with the integral of 2 pi times the integral from 0 to 16 of 2y. If we distribute, we'll get 2y minus y to the 5/4 power, and times dy. That's d. It might not look like a d, but that's d. So times dy, and then we want to go ahead and integrate that and evaluate it, and you should get a final answer of 512/9 times pi. Okay, let's look at one more example or two more examples. We'll set them up, and I'll leave you to either integrate them. Sometimes the integrals that we get using shells or even using disks and washers are beyond our calculus integration techniques at this point. Some of these actually require Calc 2 techniques to integrate. This is a very common application in Calc 2 of some of the new integration techniques that are learned in there. So some of these problems we just set up and then either evaluate using a calculator if we have one that's capable of that, or we simply just set them up and leave the problem till our integration skills catch up to be able to actually evaluate the integral using calculus techniques. Okay, let's look at y equal to sine of x, y equal to 0, and x ranging between 0 and pi, and we're going to spin this region, rotate this region around the y-axis. Okay, what I have here is a picture of y equal to sine of x from 0 to pi. And what I want to do is rotate this about the y-axis, so we're going to get a matching region over here on this side. And it is a three-dimensional object here. Kind of looks a little like a bundt cake, maybe. And so what I've got is this region. Now I want you to just think about it for a minute. If you've already done washers, this is definitely, these have holes. These are not solid discs if we were to look at it in that way. The problem with this with this example and trying to do this with a washer is washers, remember, we take the outer radius squared minus the inner radius squared. And our outer radius and our inner radius are both exactly the same function. They're both given by y equal to sine of x, which makes that a very hard problem to write out. Actually, it makes it an impossible problem to write out. So this particular problem cannot be done with the other method. We can set it up with shells. Let's go ahead and make ourselves a shell here. So I'm going to kind of put a sample shell in here. Here's one. And so there's our sample shell, and again we could have a whole bunch of them, but I want to look at the volume of that shell. Now volumes, remember, shells, 2 pi, integral. Well, where are my shells? My shells are going to start here at 0. The last shell is going to be out here at pi, so I'm integrating from 0 to pi. We're spinning about the y-axis. Our shells are stacking in the x direction, therefore our integral is in terms of x. And our radius is simply going to be the x value of that particular shell. How far is it away from the x-axis? The height is given by our function value, and the function value in this case is sine of x. Now, what we have here is an integral then of 2 pi, integral from 0 to pi of x times sine of x dx. With basic Calc 1 techniques, this is not an integral that is one that you've learned to calculate. So at this point, we would either stop in our setup, or we would go ahead and use technology or some kind of approximation technique to be able to get an approximate answer. It does require techniques that are learned in Calc 2. It does require integration by parts in order to find this integral. But if you do use some technology, you should get an answer of 2 pi squared. Okay, and that's all we can do with that particular example. Let's do one more example, and then we'll complete this lesson. Okay, so let's look at the region that is bounded by the square root of x, x cubed, and we're going to rotate that. Now those intersect at the point 1, 1, and also at 0, 0, so we have a region in between those two curves. We want to rotate this about the x-axis, so I'm going to get a matching region down here that looks like this. And if we're going to use shells, let's go ahead and draw in a sample shell. Again, if we're spinning about the x-axis, we want our shells to go around the x-axis also. So sample shell is here. Okay, so here's our sample shell. And what we want to do then is, again, here's our volume. We want 2 pi. Let's look at best integral. Our shells are stacking in the y direction. Our integral is going to be in terms of y's. So our y's range from 0 to 1. The radius of each of these shells is just whatever the y value is. Now what we need to do is look at the heights of these shells. So here's the height of this shell. This is the height. Okay, so if we look at that, that is what we want to do is find the distance from this curve, okay, this curve right here, back to the axis, minus then this distance right here. So I want to find the further distance minus the smaller distance. Now this distance this outer distance, shall we say, is given by the graph of y equal to x cubed, or x equal to the cubed root of y. So the top part of that shell is at the cube root of y, minus then the part we want to cut off at the bottom here is given by the graph of y equal to the square root of x, that's this curve, or x equal to y squared. So our height of our shell is the cube root of y, that's the furthest distance from the y-axis, minus y squared, which is the distance that is closer in, and the difference between those will actually give us the height of that shell. Now, I'm going to go ahead and write the very next step to this integral, and then I'll just go ahead and give you the answer. I assume you can integrate these by now, but we would distribute, so we're going to get y to the 4/3 power minus y cubed, evaluated from 0 to 1, all times 2 pi to get our final answer. And our final answer then is, and this will give us a final answer of 5/14 pi. Now, if you actually watched my other lesson on volumes of discs and washers, I used this same example, but did this problem with washers, and got exactly the same answer of 5/14 pi. If you've learned discs and washers, and even if you didn't watch my lesson, you might want to go ahead and try this problem, set it up both ways, and prove to yourself that you do get the same answer no matter which way you actually find the volume. The method of whether you use discs and washers or whether you use shells depends on the function values and depends on how difficult the final integral might be. Some integrals we can evaluate with simpler integration techniques, and some, as the previous example, we can't actually even set it up with one method or the other. So take some practice and good luck.